Okay, so it looks like we've got most of our group that signed up joining us. So good morning, afternoon, everybody, depending on where you are. Today we're going to be talking about a research project on pressure equalization of fenestration products done at George Brown College. So as far back as 2005, the practice of sealing the weather barrier of a house to the frame of a window in an effort to control moisture penetration was questioned enough to justify 7 years of research at the Institute of Research for Construction of the National Research Council of Canada. The guiding light that came out of that detailed scientific research was don't try to stop the wind and rain on the same plane. Few people paid any attention, but the evidence is growing to change things while residential windows still rot. So with us today, I'm fortunate enough to have the Mad Hatter of window installation, Mr. Jon Eakes. He's going to take us through a presentation, and we're going to talk about the final report that was done on this work. Before John gets going, though, I'd like to welcome Murray Frank from Constructive Home Solutions and Murray's entourage, which is on a cruise ship in Mexico. So Murray does education for builders on a cruise in the winter, kind of like Construction Disney. So Murray's got a lot of builders with him today to listen in on this research project. And Murray, it's snowing at home right now, so I hope you're having a good time. John, take it away.
Okay. Well, this whole thing is very interesting, where there's two research projects actually going on. One at George Brown College that we're talking about tonight that has wrapped up, and the other one in Winnipeg at the Red River College in their BTAC session. We don't have the final reports on that one. We'll talk about that a bit later, but they're coming out. They have done some real heavy studies on, is there a thermal penalty to stealing some insulation space in the window wall interface in order to do all the stuff that I'm talking about. So do we have a conflict with the energy conservationist guys or not? And so that'll be interesting to look at. Let's see if I can share a screen here and bring up a presentation, because I like things to be visual. And we bring that up and we'll actually turn this thing on. There we go.
Yep, we're good.
I've over time, I've come to be calling this, just for purposes of making it look more interesting, harnessing the water flow control. And I love this, harnessing the wind for water flow control. And we're limited to residential low-rise window installations, because you guys that are working high-rise, you're familiar with pressure equalization. You've been doing it forever, and it's second nature to you, and you're not questioning it. But it never got into low-rise wood frame construction, and we still have problems with moisture getting into that construction. And the National Research Council pointed us in a pretty good direction to deal with that. But we're really doing the very narrow focus of not a rain screen on the whole wall. In fact, I got into trouble with talking about rain screens, because people have their own notion of what a rain screen is. And everybody knows rain screen for walls, so they assume, well, we don't need to do any of this because we've already got a rain screen on the wall. I'm talking about a rain screen that's actually within that narrow window wall interface. It starts at the weather barrier and ends at the air barrier on the inside. And that's independent as to whether or not the siding is installed with a rain screen, which is something else. So I tend to talk more about pressure equalization than the rain screen, just to stay out of trouble on that question. Now, these are the two technology updates that the National Research Council put out, one of them in 2011 and the other in 2013. First one is on sill details, and the second one is on effective sealing practices. The National Research Council, with the Institute for Research and Construction, do their heavy duty, almost impossible to read research. And then they have a tendency to put out these construction technology updates to the public, to the industry, to summarize what the heavy stuff is all about. And they had planned 5 of these, only 2 of them came out for various reasons of budgeting and everything else. But these 2 were published. At the time they came out, I was sitting on the CSA committee for the technology, the window installation technician standard from the CSA FIT program. And I brought this to the program and they said, oh, this is far out. This is not proved yet. We don't need to get in it. We'll just stick with face sealing of the interface. So I shut up for a few years and sat back, and then finally decided that I needed to do something about it. I got invited to, actually, first of all, I decided I really needed to make it visual. I'm a visual guy. So I built a model in my shop, and it's all plexiglass, you can see here. I wanted to take it to window shows and demonstrate the principles, but it turned out it was too delicate and too difficult to fly with, and it leaked all over the place. So I ended up making a video. We're going to see a couple minutes of that video here. But just you look at this structure, there's a sprinkler rack here spraying from the siding side of this wall to the inside. There's a piece of plexiglass down the middle. That would be the weather barrier. And then there's another piece of plexiglass in the back, which would be the indoor air barrier on the indoor side. And what we're looking at is pressurizing this compartment, the window wall interface back here. Here, there's a passageway with a valve on it to let the wind go directly in. There's a place in front to put the wind into the whole thing and a pump to bring the water in. And when we do all of that, this is what it looks like looking through. There's a tiny hole, a pretty good size hole, and a hole with a tube in it that would be like foam insulation that has a tunnel. The one with the regular hole in it would be simply like a hole that would leak. The little one didn't get much through because there was too much surface tension and it took a lot of wind to blow through, but it did spit and sputter. Let's just take a look quick here. Let's plug in the wind and fill up the water and see some dynamics of this whole thing flowing. There is no wind to drive the water through the holes. Not much happens. As the flow of water happens to go over the holes in the central wall, the wind is picking up the water and projecting it freely into the inner chamber. Water is still projected inward after sealing the inner chamber until the pressure builds up. Then very little comes through. Pressure equalization. When the wind bypass is open to create some pressure equalization, only a few drops flow through the holes and down the wall without projecting inward. Take out the equalization. Take out the air seal. Removing the controls allows water to penetrate again. Now, those little scratch marks you saw on the plexiglass were because when I first built the model, the water wandered all over the face of that and didn't even go into the holes. So I directed water into each of those three holes to make sure there was water going over the face of the holes for the wind could pick it up. This is in George Brown College. Their study chamber is basically a big shipping crate that they divided with a wall, and we put 4 windows in. The windows are actually put in vertical. The camera was a wide lens camera for this shot, and it distorts it. But this is the weather side where we will be spraying water and blowing wind at it. And if you go to the inside, it looks like this. You can see now the windows are vertical. And so we have 4 windows, each of them installed slightly differently to study what's going on. We have 3 windows that are put on the face, the weather face of the wall, projected out in a standard fashion to accept strapping and siding. 1 window was recessed, so it was flush to the inside, and that was done differently. The typical inside for the windows 2, 3, and 4, which were on the outside of the wall, was to have a plexiglass installed here and caulked to the frame of the window, to the face of the frame, and caulked to the membrane, sealed all the way around. We did air tightness testing before starting, found some errors, plugged them up, and were able to do the test with a pretty airtight situation here. Then this is what the plexiglass looks like. We have 1/2-inch holes. We started with 2, we ended up with 4 that we could put plugs in, and that would allow us to turn on and turn off to various degrees the air tightness of the whole assembly. Now, there's some terminology I just got to mention, is that the CSA A440.4 committee tells me that they're constantly having trouble with distinguishing between capping and flashing. And they're trying to establish some continuity to that, saying basically that flashing can be metal or flexible membrane and is usually designed to control water flow and is usually sealed to constrain that water flow. So that's like flashing on a roof, flashing that has real flowing water all the time. Capping, on the other hand, is what we usually find around the window. It is usually metal and not a membrane, and it's always installed in a ship-like fashion to shed water. It may or may not be sealed, but if it's done well, it doesn't need to be sealed. Now, most trim around windows would be classified as capping. Now, in our study, we also added a term baffles. And for us, a baffle was any surface that interrupts a free line of sight path for airborne water. So capping around the window would be a baffle. Now, what happens when we interrupt a line of sight movement so that the rain can't just be pushed all the way into the depth of the cavity is that it hits a surface and surface tension dynamics actually come into effect, affecting all the penetrating water. Now, if we combine that with going to the backside with pressure equalization, nullifying the driving force of the wind with the wind itself on the backside, all that is left now is surface tension and gravity. So the surface tension prevents it from flowing inward, and the gravity pulls it downward to the sill where it drains out. Beautiful idea, huh? Now, here's the spray rig, a standard spray rig. We could do 2 windows at a time. And so they set up so that we could isolate the 2 top windows and then isolate the 2 bottom windows. What you see here is looking through the window, there's a pipe back over here. And that's the wind, a leaf blower, powerful leaf blower, 2 of them, blowing, moving around, variable speed. And you can see the wind is hitting that window. It's almost giving us a condition of horizontal rain. Now, here's some interesting features of this whole thing. And you can see more details in the reports as we're going through, where we see the details of each window being installed. But generally, there's no sealing between the window and the weather barrier. And you can see here a crack between the nailing flange and the wall. That's because we made our rough opening to 3/4 of an inch to give us more room to play, and especially to be able to see clearly what was going on inside. But we did not seal either the holes in that nailing flange or the crack that was there or the cracks down the side. It just was like that. In the top, every window had a drip cap. Well, the drip cap was the baffle. That meant that no water could see this crack directly. The water had to hit the baffle, went down to the windowsill, went back, hit the flange. Some of that was going inside, but most of it was working its way back out or around. There was no driving force to push it on back in. Here's a window. This one had flanges on it, but the flanges were the same as what you just saw on the top. We put 1x3 strapping over the flange and over the wall, so that became a baffle. Now the crack between the window and the 1x3 was actually baffled by the nailing flange. Even though, again, the nailing flange was not sealed at the holes and was not even joined to the wall. But no water could get in there without touching a surface and bringing surface tension into play. And here's the one box window that had no nailing flange that was put proud on the wall, and it had a line of sight that we could see the plexiglass right through. And when we turned on the water and the wind, it blew it all the way back to splashing directly on the plexiglass. So then I had our technician put on a metal flashing, just an L trim that went into the window, and you see it's stapled in 4 places. I said, no, don't do a great job of hooking it in. There's no caulking anywhere, not to the window, not to the 1x3. The 1x3 is not caulked to the wall. There's obviously water coming in from all that wind and all that rain, but it is all in contact with the surface, and nothing has a line of sight anymore. Line of sight became the critical point that we had to do to get rid of it. Now here's the sill region. This particular window was recessed. We only had one box window that was recessed flush on the inside. So we put a cap flashing on it that came from the slot. The picture doesn't show it on the proper slot, but the second one, it is in the proper slot. And we put spacers on the bottom, 1/2-inch plywood. So if you look at the right side of this picture, you can see that there are spaces wide open all along here for volume, good volume of wind to penetrate, but it has to go uphill. And by having to go uphill, it leaves the water behind. And so it gets into there, pressurizes the jambs, pressurizes the sill, but doesn't transport water with it. Some of the sills were left wide open, and they did pick up water collecting on the sill and splash it back. But as soon as we put a cap on that, even just a cap like the drip cap on the top, it all stopped and came back under control. Now here's a recessed window a bit up close. We can see all the way back to the capping. This one was fully capped all the way around with a nice dressing, what we would call trim, but it's or flashing, but we call it capping. And but you can see deep in. We'll move around it here, and you can see we could actually see pretty well what was going on inside. We even had a leak there, but it went into a dead cavity of the window, so it wasn't a through blowing of air. So, and this was true all around all of the windows, that we could see things in that fashion. Now, here's the clincher. You see this water on the bottom of this windowsill. It's the one we were just looking at. The plexiglass is sealed to the face of the 2x6 stud and sealed to the face of the window over here. There's a lighting strip that goes inside to give us good lighting on the inside. And I can see a water puddle right here. But interesting, the puddle is not spreading very far, and it's not spreading inward. Now I'm going to turn on the video. I want you to watch right here. That's the source of the water, and it's very important what is happening with that source of water. It's dripping considerably. That could be a crisis if this window was not properly sealed. But what it's doing is it's not growing because it's draining out at the same time that it's dripping. And there's no wind pressure to push it inward because that cavity is pressure equalized. Now, that's a way of seeing all of that just in video, in graphics. You can see the whole report has a number of photographs and much more detail of how it was put together. We did not set up in this project a quantitative analysis because George Brown College didn't have the facilities for that. So we relied on doing the visual proof of and the observation, because often we can get numbers from moisture meters and pressure meters and everything else, but we don't see what's happening. So by seeing at the beginning as a prelude to further research, if that needs to be done, will really help us. And getting the information from BTAC about the pressure, or about the thermal penalties of maybe all we need to do. Actually, they told me before the report was finalized, and so it's unofficial, but they told me way back in the fall of 2022, and then again in 23, that the the insulation on the outside of the glazing plane really had no effect in the thermal properties of the wall. So taking that space to make this drainage cavity can be done without compromising step 2, step 3, step 5 and codes, or where you don't have the steps to deal with and you're just in Winnipeg and it's bloody cold. You can get away with doing it to a certain point. Now, research has to be done to refine this. We've spent years refining it in high-rise construction, which I'm not familiar with. But in residential, low-rise wood frame construction, there's probably never been the financial incentive to do that. But there is a driving incentive coming in. The National Research Council research itself, the more it becomes known, the more that will be strong. We've seen more and more opening of suggestions. Joe Lstiburek was one who is proposing residential vinyl window profiles that are pressure equalized inside the profile itself. And so that would be alongside and in addition to pressurizing the window to wall interface. And the CSA A440.4 committee has already approved everything that needs to be approved for doing this kind of work and not having a complete insulation in there. And in the new version coming up, it looks like it's out for review right now, but it looks like they're going to be going even further, mandating some of this. Now, we don't know if that gets into the building code right away. All of that takes time. But I say this just to say that 4 years ago, they laughed at me and called me a Mad Hatter, and I appreciated the term. And but I still got invited back to window conferences all over just before the pandemic shut everything down. And now that the research projects have come out of the pandemic, we've resurrected the research, I think we're having enough documentation to say this is now a real possibility. What's its real potential? Notice, I have no caulking on the outside of the house. That has 2 implications. One is I have nobody on a scaffold or a ladder trying to caulk the house. And 2 is I have nobody trying to maintain the weather-beaten caulking. The only caulking bead I have is on the inside, and whether you're a workman or an inspector, you can do the entire window on a step stool in the nice sheltered zone of being inside the house. So we can look at the real possibility that we insist the membranes are wrapped all the way to the front of the cavity, and then insist that there's backer rod and caulking, independent of whatever and however insulation we put in, but backer rod and caulking right on the inside face, joining the window frame to the membrane. That's all that needs to be done. And if that is done properly, we got to beat people up to put membranes on, right? Because even in this project here, you'll look at some of the photos, you'll see that the students that put the membrane on the wall did a lot of patching work. I didn't have to worry about long-term durability, so I didn't complain. But you know, that needs to be done shiplap properly and done with as little patching as possible. But if that's our only technical complication, and then we get that indoor air barrier, I think that we have a real possibility of installing faster, cheaper, more durable, less maintenance.
Excellent, Jon. Excellent. So if anybody has questions, you can jump in the chat or you can put your hand up and we'll get you on. So Jon, this detail is becoming fairly common in the West. You know, we do see a lot of interior rod and caulk seals going into installation. So, you know, it sounds like there's some uptake here. I don't know if George is on with us or not, but like, is this getting into, you know, the updates in CSA A440 that have just been worked on and are being published shortly? Do you know if, you know, are the standards adopting what it is that you're proving here?
The A44 to this point is permitting what we suggest. The A44 that's out for review and not finalized is mandating some of it. Now, if that if it gets approved by the A440 CSA committee, that's one step. And then how much of that gets adopted by the building code? and is there regional differences or something else?
Yeah. Yeah.
I know that particularly with Murray Frank's work, uh, he's working particularly, well, he's doing it all over BC and spreading out a little bit, but mostly in the lower mainland. And he doesn't worry much about the insulation. An interesting note that I picked up deep buried in one of the IRC's technical research reports is they tested with no insulation. Now, they didn't monitor it very scientifically, but they found that that did not increase the condensation potential for the window on the inside. Now,
Yeah.
that's not like high level energy conservation project or projections, but
Yeah.
it's an indication that maybe even the therm, there's some doubt at BTEC about the therm energy efficient program, measuring or giving proper credit to the dead airspace of a really well closed window wall interface. And that if the wind blows in but doesn't circulate, that may have a better thermal factor than we think. And
Right. Okay.
but,
So Patrick from Fenestration Review, he's basically asked that question, right? So, question about thermal bridging through the insulation of the inside wall with this method. Is it a problem or has it been addressed? So you're saying there has been some research, but nothing is official out there at this
yeah,
point.
what now I don't have any access to the interim reports at BTEC. If you want to call BTEC administrator and bug them for what's going on and say, hey, we need this report, because they did a report very thoroughly in a fantastic weather chamber that was of the statue of the IRC weather chambers. And I would just love to see that report finalized. And I think it's going to tell us that, okay, if you stop at the glazing plane, there's no real penalty. And
Right. I've got Adrian Edge with Initech Windows with a hand up. Adrian, allow you to talk. You can jump in.
Hey, Jan. It's good to see the
haven't seen you for a
wrap
long
up of
time.
this project. Yeah. Yeah, it's yeah, very I love where the research has gone on this. This has been a fun ride to kind of watch this come through for the last 4 or 5 years.
Yeah,
Uh,
wait, 4 or 5 years, you a pandemic in the middle of a public service research at two schools.
you couldn't have
Yeah.
asked for a better time period for this.
Yeah, threw a wrench into that. That's for sure. Okay,
So my
Adrian, you had a
question,
specific question? Yeah, go ahead.
yeah, sorry. So Jan, going through the research, one of the things that we see out west, and I've seen in Ontario pop up, is the use of L angle at the sill for securing and for water resistance, really
Or a
acting as a
back,
back dam.
which they call a back dam of out here.
So now that you've gone through this process and have kind of seen how that attachment works, the flange method or an interior seal method, what's the viability from your point of view on using the L angle?
I think that the L is a great idea. We left it out because, well, we essentially had one because we had our air barrier was a solid piece of plexiglass. And we wanted to just see what was going on and not be hidden by a metal flange of some sort. But I think that what we did have is we had two sills that were actually open 3/4 of an inch to the blasting rain. And what we did get in those two windows was significant splashing coming in. As soon as we capped one of them, and by capped, I don't mean sealed, as soon as we put a metal drip edge on it that just let the water drip off and did not let the wind driven rain go straight in, most of that activity stopped. And so that would say that if we had an in dam, if we were to accumulate a fair amount of water on the sill plate, it would buy us more time to drain that out if we don't have a sloped edge. And I know you guys are allergic to slope sills on the West Coast. Just sharing things,
You're
how
going
they
to pick
work.
your poison, Jan.
Sharing
So
things
yeah,
Battles.
sharing things they are across country. In Quebec, when I was at the Wind Door conference in Quebec City, I saw a profile that blew me away, and I went around asking everybody, where's it come from? Walked over to the PH Tech booth, and I said, do you actually have profiles? The guys are telling me this is your profile that are 3-inch exterior extensions. And he reached over and said, you want 3 or 5 inches? And it's not an add-on, it's part of the extrusion. And I said, is this popular? And he says 20% of all our residential sales use them. And I got the feedback from the West that you can't do that. There's expansion contraction problems. It won't work. Well, they forgot to tell the guys in Quebec. So, but that means we could insulate even beyond the glazing plane because I've got 3 inches to play with. Now, we haven't done the research to say what is an optimal drainage path. My suspicion is in about 1 inch of drainage path is probably enough to stop any capillary action, any bridging over, and to small enough to fill with pressure quickly. Because if you make it too big, it takes a while for the wind to pressurize it. I remember way back when I worked with the National Research Council to build an animation on siding rain screens. They told me it takes 1/60th of a second to pressurize the entire wall of a house that has a 3/4 inch strapping for a rain screen. And because there's already air there, and all you need to do is get it up to the same level as the wind. And so they say even gusting wind is baffled. And so I think that tells us we don't want the entire space open for a drainage layer. We'd like to minimize that. We have yet to find out what's the proper distance, but some minimal size will give us maximum wind pressure and no water transport and all the water coming down. What I learned is, because I learned so much trying to talk with particularly even technicians in the labs who didn't understand what I wanted them to build. And one guy, had to get the caulking gun out because he had to seal the joints on his flashing. And I said, you shiplapped them, right? And he said, yeah, they're shiplapped. I said, then I would have rather you didn't seal it. And he said, well, we always seal it. I said, that's what we're trying to prove. Is a shiplap is good enough if we have the pressure equalization on the other side.
Right. Adrian, any follow-up?
Yeah, just 2 items to leave for the conversation. Maybe another day, Jan, is you've talked about membrane being a technical skill. That is something that obviously needs to be thoughtful. That's call it a technical barrier for a good installer.
Yeah.
I know my own personal experience with L-angle membrane installs is it greatly complicates the technical barrier there. That trying to do the wall to L-angle interface is one of the more difficult things to accomplish when you're trying to do a proper membrane lap. And then the second item that is kind of in the back of my head is water column pressure requirements. That, how well does a rod and caulk detail manage the water column pressure requirements versus what an L-angle is able to accomplish. So those are the 2 nagging questions. That would
have to be looked at. Now, if in fact we have insulation, particularly foam insulation, and then have that caulked on the face, there's going to be much less pressure hitting that caulking. So that may answer the question. It may be a simple, already done procedure that could solve that problem, if it's a problem.
Okay.
Yeah, no, those kind of details. I think if we can get the principle up enough that we can really then define a whole set of things like you're raising and say, now we have to go back to the lab, but now we're not starting all over. We're starting from a point of view that we're going to be using pressure equalization here. Now we're defining what is the size of the things we use. What's the optimization?
Absolutely.
Right.
Thank you so much, Jon.
Okay, thanks, Adrian. Jim, go ahead. Sorry, Jim, I'm not sure who you're with, but go ahead.
Turn on your mic, Jim.
Hi, can you hear me now?
Yep.
Yeah.
Okay, thanks very much for taking my question. This is clearly very valuable research, and this is something that I should introduce myself. I'm with QAI Laboratories in Vaughan.
Thanks.
I've been talking to customers about pressure equalization, normally on the subject of window design, but it's obviously well applied to window installation as well. My question is, normally when people are trying to create wind, they would either use static pressure, which is what we generally use in the lab, or they use a large diameter fan to generate the wind. That's what.
Why did we use
I've
leaf
never seen.
blowers?
Pardon?
Why did we use leaf blowers?
Well, I can understand why you would use leaf blowers, but as far as matching best practices in the testing industry, it opens the door to questions about the methodology. What is your response to that?
Right, I hear all that. One is we didn't have the facility that was adequate to really put in an airplane motor or something and blow that. But we did want to really test the kinetic energy that's involved in wind-borne rain and the variability that you don't get with a static test. And so we chose we chose first by convenience the leaf blowers, but it was also because we could pan it back and forth across the wall and up and down, and we could really create a whole bundle of worst case conditions simultaneously, because we weren't trying to quantify this wind against that result. That we weren't, that you need a static operation, or maybe you need static operation to do that, something that we could put into a chart and compare one to the other. What we wanted to see is, under worst conditions, are we going to have at any moment a worst case spreading, a penetration of water? And what happened, and it really shocked a couple of the technicians. One of them sat back and said, "My God, what's happening here?" Is that with the pressure equalization, it made absolutely no difference from no wind at all. With all that spraying all over. So I think that even though we bumped into it as a convenience for a low cost research project, it turned out to be maybe a suggestion to more sophisticated research projects to say, if you have gusting wind situation, is that, is the peak gust going to really do much of anything?
Okay, Jim, follow up to that?
No, I think you've I think you've answered the issue.
Okay, great, thank you.
Glad to hear you're doing studies on this, Jim. This is great.
Yeah, that is, yeah. Great to have the labs paying attention and listening. Yeah.
We need the contractors to be paying attention.
Yes, indeed.
Well, you need to get me to do more public stuff. You see, that's there's a joke at the National Research Council many years ago. They actually invited me in to do a training session for them on how to talk to the media. Because they're all technicians, and they were all freaked out about a reporter asking about questions. And
so they sent you to charm school. Is that what it is?
Yeah,
I gave them charm school and told them, stuff about camera.
Jim,
but I found myself in a position halfway between the National Research Council and the contractors, because they hadn't learned, except for the technology construction updates, how to talk contractor language. That would get through, at least in the residential field. I mean, it's much more sophisticated for high rise, but residential.
Yeah, for sure.
So,
Jim, thanks so much for that segue, because Murray Frank has pulled himself away from his deck chair on the cruise ship, and he has a boatload of contractors sitting with him. So, Murray, go ahead.
Unmute your mic, Murray. There you go. No.
Are you good? Can we hear you?
Sorry, it's I'm at sea. That's really good internet connection, but I think we got it there. Jon, great to see you again, and thanks for the opportunity. Really quickly, I wanted to sort of bust in a little bit on that comment about adding insulation and its effect on the outer seal. Two quick comments on that. One, we always have to be careful about how tight we make that outside. I mean, your study showed that you actually just want it baffled out there, not actually sealed. because the more effective that seal becomes on the outside, the more likely that any water penetration that comes across that pressure differential will gain kinetic energy. So, by going too far and too close to that back seal, you may actually increase the nozzle effect and spray that seal that should be dry on the inside there. And I'm always reminded of J.C. Perot from Pool Construction, PCL, way back when we started the BC Building Envelope Council in 1988. And we had him come in and do a presentation. It was pretty famous. He toured it around all of Canada. It was called Chercher la trou, or Look for the Hole. And he said the key to building science is go to the outside building and look for the hole. And if you don't find one, put it there, and go to the inside of a building and look for the holes in the walls. And if you find them, plug them up. So this concept of air tightness to the interior predates Lstiburek's, contemplations in 05. I was teaching it in 92. Got in a lot of trouble for talking about it way back then. But everything we do in our research with that insulation around there, and I'm very interested to see what happens in the Manitoba study, etc. But when we're dealing with effective R values with 2 and 3 in the window, everybody was talking about continuity of insulation from the insulated wall towards the window, and saying, well, look, this, you're going from a R15.6 effective wall and you're smashing it into just an open cavity at the rough opening. But think about it going the other way. When we were dealing with the kind of windows that we had up until we started looking at step and tier codes, going from center of glass out, the frame was the weak point in U value, in R value. And actually, that if you just do a standard buildup with the air films and the dead air space, and then consider that you got at least a Jack and King stud adjacent to that on the other side, it was far from the weakest thermal element in the build out if you thought about it from the middle of the window out. So we've always sort of taken the attitude, in those days, consider the thermal or the U value performance center of glass, and just increase the size of your fenestration to swallow the rough opening. And that basically gave us the numbers that we were looking for overall equivalent air thermal performance, R value over the whole opaque wall area. But I'd be very interested to see, now that we're looking at R8 and greater equivalency in the windows, but still that frame is the weak point. So we're looking at over insulating on the outside, because we do have a thicker blanket and we do have continuous. So I think there's something to be said for that insulating on the outside. But yeah, everything we've seen, do not seal any further inward than the center line of the IGU. Leave that as a gap so that gravity will drain the water before the water has any chance of kinetic transfer to that dry seal at the back. So those things jump out at me, but I'd really like to see some studies. Karen is sick and tired of me building experimental machines on her money. So she says, let somebody else pay for the research. I'll leave off with that.
Thanks, Murray. Jim, you've got a hand up still. Did you have another question or no?
No, that's it.
Okay, great. I see George is on. George, I don't want to put you on the spot, but do you have any thoughts on this research, and has any of it made its way into the new A444? You want to jump in or no?
Sorry, I just have multiple mute buttons here to
No worries.
That's the direction that we're heading. The standard, the next revision of the standard has just gone through an internal balloting process. And we have yet to look at the comments from that. Once that's resolved, it'll go out for public review. So I don't have the dates for that, but it should be fairly soon, because the overall goal is to try to publish the next edition this spring so that we can squeeze it into the 2025 NBC. But the general idea, what we've included for in the standard at this point, is a mandatory rain screen approach, if you will, for the rough opening gap, and no mandatory requirement for insulating the rough opening gap, at least the sill, to allow for drainage. So, and that's playing off of the research that was done at NRC, the latter report, when they were in the first hand, they were studying the effect of how do you drain the rough opening, and then the second report was to answer sort of their internal question. Well, if you take the insulation out, do you create a condensation problem? And basically, they found that that wasn't the case. Now, it was a fairly small package of research in the sense that it was only done with a vinyl window. But certainly Jan's work now adds to that, and it'll be very interesting to see what comes out of BTAC. But that is the direction that the technical subcommittee has taken on the report, and now it's out for internal review and shortly public review.
Thanks very much, George. Appreciate that. Something that I don't know if you've addressed this in any of the work that you've done, Jon, but on a flanged window, one of the things that has been a bit of a challenge in the West is you have that sill cavity as a drainage cavity, but you have the flange tight up against whatever it is, the sill membrane or whatever, and how to drain that sill past that flange. I've seen guys that penetrate the flange at along the sill, as well as shimming that bottom flange out, which can be very problematic, particularly for slider type products where you end up actually tweaking the sill, so it ends up sloping backwards.
Right.
Have you looked at that at all, or come up with effective ways to drain that sill cavity with a flange window?
We didn't look at it in terms of research. We looked at it in terms of designing our research. First of all, the IRC back in their research of 2005, etc., had the very simple solution to put round head screws in before the window, and just the fatness of the screw head would let the water out.
Okay.
And that was like a real minimum vinyl distortion that would let it drain. We looked at that and said, okay, except that won't necessarily let the wind in. And for us, we actually cut the bottom flange off of the flanged windows and left the flange on the top and the two sides, but we cut it off the bottom to leave that wide open space. Again, we really wanted, within the four installations that we had, to make a wide variety of different ways of treating that question of how do we get drainage out and wind in. So we figured if I can get wind in, we can get water out. There's plenty enough space then. And
okay.
So that's why we left two of them wide open with no flange, with actually an open space that you could stick your hand all the way in. And then we shot the rain and the wind at that. It splashed a lot. And when we put a cap over one of them that was no better than a header drip cap, that was like locked into the groove of the vinyl frame, the profile, and dropped down. We didn't even caulk the groove. You'd probably have to keep the wind from blowing it off, but we just stuck it in there to see, we'll let everything leak. And it changed the whole game. It wasn't a problem.
Interesting. Okay.
My concern looking forward is if we do start opening that up, we have to probably start look at bug screens. And if we start looking at bug screens, we know from attic ventilation and residential construction, a bug screen reduces by 50% the free airflow. And so whatever airflow we have, we need to have it twice as big if we're going to screen it.
Okay, that's interesting. Okay, that's great. We're getting close to time. So the report is final. It's 17 pages. I've had a look through it. A lot of great detail about what was done in this project. Some good photographs that really show how things were prepped and what the results were. Is there anything coming up? Well, first off, this report is going to be available on the FenCan website shortly, as well as Jon, I think you've got it on your website already.
Yes,
Is that
I have a website
the link in the chat?
that I think you'll post. That is sort of a landing page for the next steps. So
Okay, okay.
it has this one, it'll have these videos. I'll probably put this PowerPoint up. It will have the BTAC report when that becomes public. And anything else that we can draw. Actually, it has a link to Joe Lstiburek's window profiles. If you just want to take a look at those were back in 2014 or 16 or something. But so the more I get questions, the more I say I maybe have to dig further into our massive library of photographs to answer the question. And
Right,
if
sure.
that
Okay.
happens, we'll be posting all of that on the website there. So that one page will be sort of a follow-up page with anything else that we might be able to dig up, or any new research that we put together. Because I think if we're going to do a further research, or if we have to redo some of the stuff from BTAC, that what we want to do is do it with a larger industry participation at defining the research, so that everybody can get their little question in up front. And that might help us to make even a better, stronger research project.
Excellent. Well, we were happy to work with you on this and to support this research. There's a lot of changes going on in the fenestration world when it comes to installation.
I should mention that Fenestration Canada did financially support it, as did SAWDAC.
It was great project. Lots of really interesting information and results coming out of it. So we appreciate your work. So everybody, you can go to Jon's site there in the chat. He's put the link to the site in the chat. You'll be able to find a lot of this information. The report will be up on the FenCan site shortly. This session is being recorded and will be available on our YouTube channel, as well as on the Fenestration Canada website shortly. I do want to thank our sponsor for this session, OpenJanella Software. They've been a great sponsor for a lot of the work that we do. So appreciate their support. And that's pretty much time. Jon, thank you so much for coming on. Great stuff, really interesting. I think we're changing a lot of minds about how products should be installed and managing air and water flow. So appreciate your time. Thanks very much. And we're going to call that a day. Thank you.